talk is discrete-time ocean ecosystem dynamics. The talk is first a 3-variable ocean ecosystem and a 6-variable ocean ecosystem. Consists of 2 parts. In this work, it was considered the first successful ocean ecosystem model, which is closer to nitrogen, and it is illustrates interaction between 2 kinds of plankton, such as phytoplankton and zooplankton. Let N be concentration of nitrogen available for uptake and measured as mass per unit surface area, and respectively P and Z concentrations of phytoplankton and zooplankton in this considering area in the ocean, and nitrogen is taken from the ocean and incorporated into phytoplankton, and at the time zooplankton by zooplankton phytoplanktons incorporated, and when they die, planktons die, and when they die, then they will be nitrogen. This cycle is given as following system of differential equations, where the parameters A, B, C, D are real numbers, and sum of all equations is 0. It means that the sum of all variables constant number. In other words, it means that for this system, law of conservation of mass for nitrogen is satisfies. First, we give the discrete version of the model of this model. It is the following model. For simplicity, we denote the variables z, p, and n by x, y, z respectively. Then the main definitions. The quadratic stochastic operator is a mapping of the standard simplex defined by the formula 3 into itself of the form 4, where the coefficients p, e, j, k satisfy the following conditions. First, they are non-negative and symmetric with respect to indexes I and j, and sum of their coefficients by k equal to 1. This is definition of quadratic stochastic operator, and the definition of L-Walter operator. Thus, each quadratic stochastic operator can be uniquely defined by the cubic matrix, which consists of elements coefficients p, j, k, and fix L, and assume that p, j, k satisfy the following additional conditions. First of all, p, j, k 0 if k non-equal to I and j for any k from 1 to L, and p, j, k greater than 0, strictly greater than 0, for at least one pair I, j, and for any k from L plus 1 and to M. Definition: for any fixed L from 1 to M, the quadratic stochastic operator defined by 4 and coefficients satisfying the conditions 5 and 6 is called L-Walter quadratic stochastic operator. Particularly if L equal to M, the L-Walter operator will be is called Walter stochastic operator, and like these operators well studied by the authors Ganekhajayev, Rasul Nabiyevich, and others. L-Waltera stochastic operator firstly defined in this work published by the author Rozikov and his student. Note that considering operator has the form 2-Waltera operator, but parameters not related to PJK. It means that parameters not satisfies
Sobirjon, maybe not reduction, but reduction.
Reduction, yes.
Reduction. This, reduction.
Then using this equality, x plus y plus z, without generality, we can assume that sum of their equal to 1, and using this equality, we have the following proposition. The operator 2 maps two-dimensional simplex into itself if and only if the parameters satisfy the following condition 7. Moreover, under this condition, the considering operator is 2-Waltera quadratic stochastic operator. The main problem in dynamical systems, we know it is the limit behavior of the trajectory for any initial point. This theorem is for this condition. This theorem, this theorem, we give a limit behavior of the trajectory for this condition. Theorem: if parameters C and D satisfy this equality, then for any initial point from the simplex, we have the following. Here, there are many conditions for parameters, and for some cases, limit point can be depend to the initial point. And the next case, which this
in previous theorem, so you are considering all possible
yes.
conditions for parameters.
Yes, so all possible conditions were considered. Yes.
So this is full description of limit.
Next case, when the multiplication is non-zero. In this case, first of all, we found the fixed points and defined their types. Proposition: the operator 2 has the following 3 fixed points: lambda 0, lambda 1, and lambda 2. Moreover, we have additional conditions for parameters for saving these fixed points in the simplex. Before defining their types, we consider reduction this operator 2 into operator 9. Here again, we use this equality, and we have the following operator with 2 variables, x and y. Note that here x plus y less than 1. It is easy to see that for this operator, the following points will be fixed points from this previous proposition. Definition: the fixed point for the operator f is called hyperbolic if the Jacobian matrix of this operator at the fixed point has no eigenvalues on the unit circle. There are 3 types of fixed points. First of all, fixed point P is called attracting if all eigenvalues of the matrix GP less than 1 in absolute value. Repelling if all eigenvalues greater than 1 in absolute value. Otherwise, it is called a saddle fixed point. This proposition is about the types of the fixed points for the operator W. proposition. The following relations are true. First, lambda 0 is called non-hyperbolic, will be non-hyperbolic if parameters satisfy this condition or this condition. Just maybe attractive if a greater than 0, maybe saddle if a less than c, greater than c, less than c. For the fixed point lambda 1, also it can be, it will be 3 type, non-hyperbolic, attractive, and saddle fixed point for some conditions, 2 parameters, and lambda 2 maybe only non-hyperbolic and attractive fixed point. And this theorem is more general case that if let this multiplication non-zero and lambda 0 will be any fixed initial point, then the following 3 cases hold true. First, if c less than a, then the limit of the trajectory, limit point of the trajectory is lambda 0. If c greater than a and d less than b, then 3 cases may be obtained. First of all, this fixed point, this is also fixed point for the operator, lambda 0 and lambda 1. And last case, if c greater than a, the greater than b, and both of them greater than 0, then it's possible 3 cases, lambda 2, lambda 0, and lambda 1. These obtained results published in this journal in 2019, International Journal of Biomathematics. Let's consider the operator 9 for the concrete values of the to the parameters. That if we take these parameters in this form, then the operator has the form 12. This operator has the limit point for the initial value 0.1 and 0.3 and 0.2, 0.2 respectively. This is a red trajectory. Red trajectory is the trajectory of initial point 0.2, 0.2. Green one is from the initial point 0.1 and 0.3. And next part of this talk, last studies showed that in the ocean it is very important third type of the plankton. It's called mixoplankton. And moreover, in the ocean, the bacteria also very important for the dynamics of the ocean ecosystem. In this work, which is published in 2016, the interaction between planktons, bacteria, and dissolved organic and inorganic matters. So this cycle is summarized in this following diagram. This is phytoplankton, which is incorporated by zooplankton and mixoplankton. If they die, then it transformed to the organic matter, dissolved organic matter, and organic matters incorporated by bacteria and transformed to the inorganic matter. At the same time, phytoplankton and mixoplanktons feed inorganic matters. We with Professor Richard Varro and Rosie Cook, we tried to model this cycle and study it mathematically. Before this, we denoted the vertices of the graph by A1, A2, and A12. Each one is the transfer rates between the different compartments. And moreover, for simplicity, then we have had the following system of differential equations. Obviously, for this system also, sum of all systems equal to 0. That means that law of conservation of mass is also satisfied for this system with respect to organic and inorganic matters. We note that the study of the role of mixoplankton is very recent, and the system is not analytically studied yet. To the best of our knowledge, the research work is a first exploration of the field. For simplicity, we denote the following variables by x1, x2, and etc. x6. Then we have the following discrete-time version of the considering ocean ecosystem model. It has the following form. Proposition. We have that this operator maps a 5-dimensional simplex into itself if strictly positive parameters satisfy the following conditions. All conditions denoted by 15. Moreover, under their conditions, considering operator is 4 Volterra quadratic stochastic operator. Fixed points of this operator. The operator 14 has the following fixed points with conditions to the parameters 15. First, lambda 1. Here the lambda is any number from 0, 1 from this segment, and lambda 2, lambda 3. There are some conditions to parameters for satisfying that fixed point saves in the simplex, stays in the simplex. Lambda 4, lambda 5, and lambda 6 and lambda 7. That we have found all possible fixed points for this operator.
Sorry, so in the first case, you have a continuum of fixed points, yes?
Yes, a set of fixed points. We can say set of fixed
continuum.
points.
Mm-hmm.
Yes, continuum.
Okay. And in the case 4, also continuum. Lambda is arbitrary.
Not arbitrary. Sorry.
Case 4.
For this case, lambda yes, must be defined in below. I'm sorry. This is concrete value.
I see. Okay.
Thank you. And next, the limit behavior of the trajectory. First case no dissolved inorganic matter in the ocean. In this case, we have the following proposition. For an initial point lambda 0, which is satisfies the following condition, the trajectory has the following limit. This limit is the element of the first fixed point set. Second case, in the ocean, there is no dissolved organic matter. In this case, if the trajectory is initial point taken from the simplex and this additional condition satisfies, then the trajectory has the following limits. For this case, the limit point is also 0, 0, 0, and 1. For the second case is second fixed point lambda 2. Next proposition is for the case no bacteria. Proposition. For any initial point from the simplex, the trajectory has the following limit. Note that in the limit, the lambda bar is depending to the initial point. Next case no phytoplankton. Before giving the theorem, we have the following two lemmas. First, for an initial point lambda 0, if x4 sequence converges to 0 and two among these three sequences also converges to 0, then third one also converges to 0. In addition, the trajectory converges to the fixed point lambda 1. Next lemma, for an initial point lambda 0, if parameters satisfy the following conditions, respectively this condition, then x4, sequence x4 converges to 0. Next proposition, if parameters satisfy the following conditions and for any initial point lambda 0 with 0 coordinates in the first coordinate, then trajectory has the following limit. Here also lambda bar depends on initial state, initial condition. Next proposition, case neither zooplankton nor mixoplankton in the ocean. In this case also, if parameters satisfy first and second conditions, then for any initial point, trajectory has the following limit. For more general case, we have the following proposition. If parameters satisfy these conditions, additional conditions, for any initial point from the simplex, the trajectory has the following limit.
Except 6 fixed points, yes?
Yes, this is first fixed point. Here also lambda bar depends on initial state. These taken results also published in this journal with co-authors Rozikov and Richard Warrow. To be more clear, we give the following example. We take the parameters as following form. These parameters satisfy the conditions of the last proposition, and corresponding limit point is here. First, 4, 1, 2, 3, 4 means that first 4 coordinates of the limit point and last 2 coordinates growing up in this picture, in this figure. If in this case, if initial state changes, then the limit point also changes. You can see in these pictures also, or these pictures. Only we have changed the initial state, but consequently the limit point also changes. That's all.
Yeah. So please, any questions?
Biological interpretation you plan to give, but
Yes.
I don't see here.
What is biological explanation or interpretation of this result?
Yeah, for each results, we gave biological interpretation also in the paper. For example, in this case, if parameters satisfy the following conditions, then after some time, then all planktons and bacteria disappear and leave only dissolved organic and inorganic matters depending on initial state. This is biological interpretation for this proposition.
So first types vanish, yes?
Yeah.
Mm. Okay. But is there any other cases when they do not vanish?
Yeah, in this, for our results for each proposition, the living organisms disappears. Only
Disappear.
yeah, disappear. Yeah.
So it's very bad models for
Very poor. Yeah.
organisms. I see.
The question from Nizhny Novgorod. Your input equations, your primordial equations, looks like the well-known SIA model for diseases. Have you? Yes. Have you tried to investigate this analogies between models of diseases and your models of ocean plankton?
Thank you. I have tried to compare my model and the epidemiological models, and they have difference. And I also studied the epidemiological models such as CEC and SAIR models in my dissertation. The meaning, the coefficients and the form of the equations are totally different in this case.
But what about dynamics? Dynamics is the same, or it also
for example, for first system, the dynamics, the system is regular, converges to the fixed point for any case. In the models, epidemiological models also like this, regular.
Okay, thank you. More questions? Есть вопросы еще? No questions. O'tkir, sizda kommentariy yo'qmi?
Yo'q, hammasini yaxshi o'qildi. Faqat endi mana bu oxirgi modelni ko'ryapsizlar, 12 ta parametri bor. Shuni erinmasdan hamma hollarni ko'rib, suluchi qilib o'rganib chiqdi. Ancha yaxshi ishladi. Mana Fransiyaga borganda ana o'qilganda, ana Varro bilan birgalikda model kiritishgan, unda yaxshi o'rganib ana o'qildi. Yaxshi emas.
Maqolaga chiqgan. Maqolaga
ana ko'rsating ana maqolani. Non-linear studies'da chiqqan. Мавзусида.
Рахмат. Есть ли еще вопросы? Вопросов нет. Так, спасибо. Так. Джабр, следующий у нас докладчик.
Keyingi dokladchi Santiago universitetini ilmiy xodimi Pilar
Qaysi universitetda?
Santiago de Compostela.
Santiago de Compostela.
Manimcha o'zi ham qatnashyapti shu yerda, o'sha Pilar Pias.
Erkak kishimi?
Ayol kishi, qiz bola.
Yo'q, qiz bola.
Pilar, are you here? Eshitmayapti.
Pilar.
Boshda bor edi.
She is reading. She
Ha, shu yerda ekan.
yes deb yozdi.
Yozyaptim.
Yozyapti.
Yo'qdirdi. Okay. Then next talk is Pilar Pérez from Santiago de Compostela. So the title will be announced. Okay. Если других вопросов, предложений нет, тогда На этом закончим. Спасибо всем. Будут желающие, записывайте, подавать заявки. I'm now in University of Vienna. Okay. I see.
Bizda yana ikkita zaявka bor. Bundan tashqari 17-oktyabrga Qurbonboyev Tuyilboy, 24-oktyabrga Artyom Platkin degan Braziliyadagi Braziliya universitetidagi bitta professor zaявka bergan.
Okay.
Artyom Platkin.
Okay. Okay. Pilar, I see you. Nice to meet you. See you next week. Okay. So now we finish our today's seminar. See you next Monday at the same time. Bye-bye.
Jobran o'zi sovet nishni nima qilaylik? Jobran o'zi qoling, gaplashib olaylik, kengashish.